My name is Dima Smirnov, and this is work done with Justin Solomon at MIT and Mikhail Besmeltsev from University of Montreal. We propose a fully self-supervised method for learning a patch-based representation of piecewise smooth, manifold 3D geometry. This representation is sparse, interpretable, and easy to edit, making it a convenient choice for downstream tasks in design and modeling. Past deep 3D shape representations are fundamentally incompatible with standard CAD modeling tools. For instance, representing geometry as a voxel grid or octree is expensive to store and difficult to edit. Point clouds are more compact but contain no notion of topology. More recent approaches that model shapes using learned implicit fields are high fidelity but are difficult to store, render, or edit. Abstracting shapes using simple explicit primitives, like cuboids, does not capture fine details. Finally, works like AtlasNet produce collections of learned patches that have no notion of connectivity and cannot be edited in an intuitive way. We propose the first learning-based system to predict parametric surfaces of CAD objects. With our framework, we can train a deep network to input, say, a pencil sketch, and output a collection of parametric 3D patches. These can then be loaded into conventional CAD software and refined by editing control points with just a few clicks. Our system directly predicts a CAD model composed of standard parametric patches, such as these Koons patches. Patches are described by their control points, which also serve as intuitive handles for editing the geometry. We represent a shape as a collection of Koons patches, whose topology and rough geometry are defined by a deformable template. Our network outputs control points corresponding to deformations of the template. In our work, we introduce a method for automatically producing such templates. For a given category of shapes, we start from a collection of cuboids that exemplify a typical model. These can be obtained from bounding boxes of a segmented model or placed manually. We first subdivide the cuboid faces to obtain a valid quad mesh, and then we iteratively merge faces to reduce the number of elements. We automatically construct a separate template for each shape category in our experiments. Additionally, we show that our method even works with generic sphere templates, which provide patch topology but do not offer geometric priors. Our main loss function is inspired by chamfer distance, a common differentiable metric between shapes. Chamfer distance treats the source and target geometry as point clouds, measuring the closest distance from one to the other, and vice versa. A naive way to use chamfer distance to compare a mesh and a collection of patches is to uniformly sample the patch parametric domain, uniformly sample the mesh, and compute chamfer distance between the two point clouds. Sampling uniformly in patch parameter space, however, yields a point cloud that is not uniform with respect to surface area. Therefore, we get a biased value for the chamfer distance integral. Instead, we pull back the surface integral to the parameter domain, the unit square. By computing area weights, that is, the Jacobian determinant, in closed form, we get an unbiased evaluation. Here we demonstrate our representation on the task of sketch-based modeling. Our system inputs a sketch, encodes it using a deep network, and outputs parameters explicitly defining the Koons patch geometries. In addition to area-weighted chamfer loss, we propose several other differentiable priors that improve our results. In order to have a fully self-supervised pipeline, we render mesh contours, vectorize and augment them, and pass them through a pencil stylization model to get paired 3D geometry sketch image data. Note that we do not have ground truth decompositions of the 3D meshes into Koons patches, and our loss function does not need this supervision. We show our results on the knives, cars, and guns ShapeNAD categories. For each example, we show the input sketch, the 3D model obtained using a generic sphere template, and that obtained using a category-specific template. Here we show results on some more categories. As an additional application, we compared to standard CAD software in converting a mesh into a collection of NURBS patches. Our method is several orders of magnitude more parsimonious, and our patches are placed consistently. Across different models, the same patch captures the same feature. Additionally, we can interpolate between distinct 3D models, either by linearly interpolating the Koons patch parameters or by interpolating in the learned latent space. While the results are similar thanks to the consistent placement of patches, latent interpolation incorporates some shape priors learned from data. In conclusion, by carefully formulating differentiable loss functions in terms of parameters that explicitly represent geometry, and by introducing a pipeline to synthetically generate realistic training data, we design a novel, self-supervised method for shape reconstruction. We produce detailed 3D models that are defined using consistently placed primitives that can be intuitively edited with standard tools.